Hello, my access to HE Newblets. Today is New Year's Day 2023. You might think I'm absolutely mad recording this, but I got a nice shiny HD microphone for Christmas, and I've been meaning to record this for several years now, and I thought what better chance and time to sort of record this. This is a fundamental sort of GCSE chemistry lesson. Ooh, I know you're running for the hills when I say that, but it's fundamental because it underpins the stuff that we're going to learn in the biomolecules unit. And if you don't understand this, then you're going to be completely befuddled and confused about what you're learning about in biomolecules. It is a GCSE level, and I don't think it's anything too technical, but it's not part of the actual course. It's not part of the unit that we need to actually teach, but I do feel like that access learners generally don't understand this properly and therefore don't have a very good grounding about how things join together, and I'm not going to give too much away. So without further ado, let's go into it. What do you see? What am I? Well, I wouldn't hold it against you if you didn't know what you were seeing there. Not many people would. You might obviously see that this is some kind of atomic structure. You might know that the C stands for carbon and the N stands for nitrogen. And if you don't worry, because it doesn't matter at this point. I'm hoping by the end of it, you might know what you're seeing. And this will then lead into our next topic and our next main topic in biomolecules. So it's no surprise that we're going to be talking about atoms, and this is a concept that has been going on for centuries. In fact, Democritus was sort of the first person, I think, in my mind to sort of bring the notion up. And he was sat under a tree one day with an apple and a knife, and he thought to himself, I wonder how many times I can chop this apple in half until I don't have an apple anymore, or I can't chop it into any more smaller units. And he knew that obviously he didn't have the tools to do that, but only in the last the last 3 centuries, 17th century, that we've been documenting the different bits because of technologies available to sort of break down things into its smallest components. So the first main concept really to understand is that everything is made up of matter, and matter is made up of atoms. So whatever you're seeing now or touching, the desk, the carpet, your hand, the tree outside, is all made up of atoms. So everything is made up of atoms. A cell, a mitochondria, a cell membrane, a nucleus, your genetic material, they're all made of atoms. And those atoms that we know of are documented in something called the periodic table. Now, I know you're probably running for the hills at this point because you saw it in chemistry lessons in school and probably didn't understand the word it was saying. But these technically are the things that scientists have broken down into the elements that make up matter. So these are the different elements that make up matter. So for example, you've got hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, blah, 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 blah. Scientists have put these atoms, these elements, into a table so that they can demonstrate similar properties. That's all I'll say. We don't really need to know the periodic table, but that's just what they're presented in. So the human body, for example, is made up of 6 of these elements. So 99% of the human body, that's 99% of the human body, is made up of just 6 of these elements. So if you think about it, you pick yourself apart with some atomic tweezers, and all you'd have is a pile of carbon, hydrogen, nitrogen, and the 3 others, which are my name escapes me, and it might be in a slide later on. So when we look at these structures, these atomic structures, you're thinking you just want to probably barf on your desk right now or wherever you are. But if I ask you what you see there, It's a molecule that you have talked about in cell biology, and hopefully you can see that head and two tails is a phospholipid that you've already talked about in cell biology. Now we draw it in a nice head and two tail shape, but actually the head and two tails are being created by the structures of those atoms within that molecule. And those structures of those molecules give the let's say this phospholipid its properties. Again, maybe what you see, we haven't talked about this specifically, but it becomes DNA. So that is the structure of DNA. So why do we need to know them? Because they make up stuff. And this is what I talked about earlier, in that 99% of the human body is made up of just 6 elements: oxygen, carbon, hydrogen, nitrogen, calcium and phosphorus. Which is really crazy, I think, if you just sort of think about it. So you should sort of, I don't know, take your foot off, chop your foot off. Everything else is made of carbon, these 6 elements that you can see on the screen. Which blows my mind, really. And so why do you need to know about it? Is because the way that these atoms join and combine together give these different molecules their different properties. So how is a heart different to a lung, different to a skin cell, different to a liver cell, whatever? They're made of the same stuff. It's just that they're constructed in different ways. So what you need to know first of all is the structure of an atom. Now this is the planetary model, and it's a very 2D structure. The chemists amongst us will be shouting at the screen saying this is not actually how it is, but it's the best way of learning the structure of an atom. So you can see this thick black line around the inside. That's called the nucleus. And within the don't confuse that with the nucleus of a cell, right? Nucleus, I suppose, is given the term because it's right in the middle. But the nucleus of the cell is made up of these positive charge molecules called protons, and these hollow circles here, which are neutrons, which have a neutral charge. And then what you have here around the outside are these circles. So you can see the 2 circles, the 2 big circles around the nucleus. Now they're referred to as orbits, or I call them shells. And on those shells you get electrons. Well, that's not very good, electrons. Okay, which have a negative charge. So up here in the top right, protons have a positive charge, neutrons have a neutral charge, and electrons have a negative charge. Okay, I'm not bothered about the mass. So in this atom here, there are how many protons? 1, 2, 3. There are 3 protons in the nucleus. There are 1, 2, 3, 4 neutrons in the nucleus, and there are 1, 2, 3 electrons in this atom. All right, so there are the same number of protons as there is electrons. All right, now when we look at the periodic table, you'll have certain numbers next to the type of atom it is. So we can see that this number 3 here, which is probably the most important number I find, is something called the atomic number. And the atomic number tells you the number of protons in the nucleus. The number of protons in the nucleus. So the atomic number of an atom is the number of protons in the nucleus. The 7 tells you the atomic mass of the nucleus. So that is the number of protons and neutrons in the nucleus. So the number of protons and neutrons in the nucleus, which would be 7. Right, so the atomic number of Li, which is lithium, is the atomic number is 3, which has 3 protons in the nucleus, and then its mass is 7 because it also has 4 neutrons in the nucleus. So the atomic number is the number of protons in the nucleus. The mass number is the number of protons and neutrons in the nucleus. Okay, so that's the basic structure of an atom, and all different atoms have a different number of these things in the nucleus. So for example, hydrogen will have helium will have 2, hydrogen will have 1, and so on. So that's this atomic number does not change. This atomic number here does not change, and that's how you identify what kind of atom you are dealing with. Now, the only thing that can change is the number of electrons. So these are quite fickle, and they can be given or taken. So if we delete this electron here, so if it's given away, so if it goes off this orbit, then suddenly you've got 1, 2 electrons, which are negative, and then you'll have 1, 2, and 3 positive protons. So 3 positives and 2 negatives means that you've got a positive charge, because you've got 3 positives and only 2 negatives, which means you've got a positive charge. And we call that, any time where the electrons are different to the protons, we call that an ion. So in an ion, the number of electrons is different to the number of protons. And the same will apply opposite. So if this atom picks up extra electrons, let's say there's a 1, 2, 3, 4, 5. So if there's 5 negatives and only 3 positives, that means that this is a negative ion. It's still lithium, all right? So it's still lithium, but it's lithium, and you might have seen it in textbooks. So lithium with a minus charge would be like that. Lithium with a positive charge would be like that. It's just a different amount of protons and neutrons, protons and electrons, so to say. In an atom, in a sort of neutrally charged atom, the number of electrons is the same as the number of protons. So if you've got 3 positives and you've got 3 negatives, you're going to have an atom. If you've got 5 protons, which are positive, if you've got 3 electrons, that's going to be an ion. All right, it's still technically an atom, but an ion is a charged atom. Okay. So here we have different atoms that are found on the periodic table. So here you've got helium, number 1. So you've got 2 protons and 2 neutrons with 2 electrons on the first orbit. Now, one of the things that this slide is useful to see is that there are only a certain amount of electrons can fit on each orbit. So you'll see that the first orbit, even in whatever atom that you look at, whether it's atom 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, you can only fit 2 electrons on that first orbit. So if we're looking at number 9, there are the 2 electrons on the first orbit. You can't fit any more electrons on that first orbit. Now, the next question is, well, okay, once that's full, you start another orbit. So, for example, if you can see number 4 over here, there's the first. Sorry, I should do it really in a different colour, shouldn't I? That'd be better. Let's do it in red. So there are the 2 electrons on the first orbit. So we've had to start a new orbit, and you can see here that there's 2, 4, 6, and 7 on the outer orbit, but together there's 2, 4, 6, 8, 9 altogether. 2 in the first orbit, 7 in the outer orbit. So you can see the electrons around the outside there is 9, right? So the second orbit can fit 8 on, and so can the third orbit. So if that second orbit fills, then you start another orbit, which then can fit another 8 on. And it does get stupid, so we do get more and more, but we only need to know those, the first 3 orbits to 8, which takes us to the periodic table of 18, which is perfectly fine for us. All right, so what I'd like you to do is to look at atom number 3, let's say atom number 3, and atom number 5. And what I'd like you to do in your own notes is to fill out what the atomic number is for each, what the mass number, the number of electrons, and whether it's an atom or an ion. Okay, so you pause the video in a few seconds. See if you can work out what the atomic number is, the mass number, the number of electrons, atom or ion, and the same for atom number 5. So 3 and 5. Pause the video in 3, 2, 1, go. Okay, hopefully you got it right. So for atom number 3, there are 7 protons in the nucleus. So 1, 2, 3, 4, 5, 6, 7. Good. The mass number is the protons and neutrons. So there's 1, 2, 3, 4, 5, 6, 7 hollow circles in the middle. So the mass number is protons plus neutrons, which gives you the mass. The number of electrons are out the side. It's 2 on the first shell, and 2, 3, 4, 5 on the outer shell. So 2 and 5 is 7. So 7 electrons, and this is an atom because there are 7 positives and 7 negatives. So we've got an atom. Okay. And the same goes for number 5, really. I'm sure you did it right. You can hopefully see what happened, but that's essentially the structure of an atom and the structure of an ion. Interestingly enough, I'll draw your attention to one of the ions then. Let's go for atom number 11. There's the atomic number 12, so there's 12 positives, but there's only 10 negatives. So there's more positives than negatives, so it's a negative ion. So that would be a negative ion. 12 positives and 10 negatives. Whereas this one, here the number of electrons, so atom number 12 is 10, and there's 10 negatives, should I say, and then electrons, and then there's only 8 positives, so that gives you a negative ion because there's more negatives than positives. Okay, good. Right, so let's have a look at how atoms bond together. How do they join from one to the next? So they bond when 2 or more atoms join together. For example, here you've got H2, 2 hydrogens, CO2, carbon dioxide, H2O, water, and C6H12O6. A bit more complicated, but what you're looking at there is the chemical structure for glucose. And what that means is that you've got 6 carbons, 12 hydrogens, and 6 oxygens in that glucose molecule. You just count them all. CO2, 1 carbon and 2 oxygens. So how do they join together, and why do they join together? Well, there are 2 different ways that atoms can join together. Well, the first is ionic bonding, and the second is covalent bonding. So let's have a look at the introduction. Most atoms want to be happy. For atoms to be happy, they like to have their outer shells full. So if it was that first shell, remember it can fit 2 electrons on, so it wants to really fill that shell if that's the outer shell. If it's got 2 shells, it wants 8 on that shell, and if it's the third shell, it wants 8 on that. It wants its shell full. Some atoms have too many and like to share their electrons. Some atoms have too few and go around searching for extras to try and fill their outer shells. So let's have a look at something called ionic bonding. Now you know what an ion is, yeah? We've just done that. You know what an ion is. What is it? It's an imbalance between the positive protons and the negative electrons. So here we've got fluorine, and the atomic number for fluorine is 9. So there are 9 protons in the nucleus, 9 positives, and outside it has 9 electrons. Should I say, it has 2 electrons on the inner shell, and then it has 7 electrons on the outer shell. So it's missing one. It needs to pick one up to fill its outer shell. All right, and once it's picked one up, it'll be really happy. So when it's put in the region of a sodium atom, the sodium atom has 11 protons in the nucleus, and it has 11 electrons. So it'll have 2 electrons on the first shell, 8 electrons on the second shell, and it has 1 electron on the outer shell. So ionic bonding is when electrons can be passed and shared over. So what happens if this electron here were to fill that outer shell? This would be happy, and this would be happy, because they've just filled their outer shell. So by losing this one, it actually exposes this second shell as being full. 8 has been full. But when this sodium loses its electron, it suddenly has only 10 negative electrons, 2 on the first shell, 8 on the second shell. But initially in the nucleus it has 11 positive protons in the nucleus. So sodium would therefore become, guess, positive, because it's got more protons than electrons. But on the other hand, fluorine did have 9 electrons. It's now just picked up 1 extra, so it has 10 electrons, and initially it had 9 protons. So fluorine has now become a negative ion, and because they now have a charge, because they're now an ion, these 2 atoms fall in love with each other.
It's your mom!
Oh no, my mum just called. Classic. But where was I? Because these atoms have a charge, it now means that these 2 atoms fall in love with each other and they want to join together. And that's what atomic bonding means, is that when atoms have a charge, positive and negative, then they link together like magnets. And by giving and taking electrons, it means that atoms can gain that charge. They can either gain electrons, which means they'll go negative, or they can lose electrons and become positive. So that's one way in which atoms can bond. The next type of bonding is something called covalent bonding, and this is where atoms share 1 or more pairs of electrons. So the sort of more basic sort of example would be, let's look at H2O. So here we've got, let's start with a nucleus of oxygen. So the atomic number, if you go back to the periodic table of oxygen, I'm led to believe, off the top of my head, I should have been more researched, that is 8. So it'll have 8 positives, protons in its nucleus, which means we're going to form 8 electrons around its orbit. So let's put the first 2 electrons in the first orbit, which is full. So that shell is full. So then we put 6 on the outside. 1, 2, 3, 4, 5, 6. Don't worry about where you put them. Doesn't really matter that much at our level at this point in time. So that's oxygen. Its atomic number is 8. So therefore it has 8 electrons usually. So 2 in the first shell, 6 on the outer shell. Now you can see that this outer shell is not full. It's got 6 on, and there's 2 empty spaces. It needs to pick up 2. So where do the 2 come in? Well, let's look at what colour do I want to give it. Let's look at red. So here is hydrogen. Hydrogen has an atomic number of 1. All right, let's draw hydrogen up here. So there is its nucleus, and it has an atomic number of 1. So it has 1 electron on the outside, and it has 1 proton in the middle. Now you can see that hydrogen is also not full and therefore not happy. It needs to pick up another electron to make it full. So what happens is this hydrogen shares its electron with oxygen. So that red line there is the hydrogen atom that I've put, and the red circle which I'm shading you now is its electron. So you can see now that the hydrogen atom, with the way it's shared, now has 2 electrons on its outer shell because it's sharing the electrons with the oxygen, which is now a happy atom and very stable. But when we add up the amount of electrons around the outside of the oxygen, there's only 7 now. 1, 2, 3, 4, 5, 6, and 7. So it needs to pick up another. So let's include another hydrogen atom on its outer shell to share. And now we have that magic 8th electron around the outside shell of the oxygen, and we also have 2 electrons on this hydrogen. So we've got 8 around the outside of the oxygen, 2 around the outside of the hydrogen, and 2 around the outside of this other hydrogen, which means that all of those atoms are really happy because they've got full outer shells. And what you've got there is H2O. H2O. And that is covalent bonding, and it's much stronger than ionic bonding, and lots of our bonds in our body are covalent bonds. It's where atoms share their electrons to fill their outer shells. So here's a bit of an extension task for you to have a go at, and I think only a few of my students have been able to do this off the top of their heads, applying it. But what would CO2 look like in terms of the electron structure? How would they share their electrons so that their outer shells are full? And it's sort of like a Sudoku puzzle. Have a go at it and sort of engage with it and see how CO2 would look. So carbon, there's 1 carbon in it, and carbon has an atomic number of 6, and there are 2 oxygens in the molecule which have an atomic number of 8, as we've just seen. So 1 carbon, 2 oxygens. How do they share their molecules, or the electrons should I say, to become a happy atom, or a happy molecule? An atom is just 1 element on its own, so that's just one, like 1 carbon, 1 oxygen, 1 hydrogen. A molecule is when they join together to make bigger things. So I'm going to pause the video, have a go at it, and I'll show you the answer on the next screen. Don't peek your head. There we go. There's the answer. So you can see that the carbon molecule is in the middle, and I think that if I there's the first 2, so it has a atomic number of 6. So let's track its 6 electrons. So 1, 2, 3, 4, 5, and 6. They're the carbon electrons in the sort of equation, if you like. And there are 8 protons in oxygen. So 1, 2, 3, 4, 5, 6, 7, and 8. And the same on this side, 7 and 8. So you can see that if we count up their outer shells, 2, 4, 6, 8. 4 and 4 is 8 for the carbon, and then 4 and 6, 4, 6, 8 for this other oxygen over here. So happy atom, happy atom, happy atom is what CO2 looks like. What what was I going to say? This is called a double covalent bond because they're sharing a pair of electrons rather than just one. So it's a little bit of a trick. If you didn't get that, I'm hoping you worked it out, but let's by the by. Now, one of the things that's really important, I think, when we're forming molecules is that carbon's really important. You can see that carbon is like one of those multifunctional stickle bricks that I used to have as a kid. Is that you can fit something here, you can fit something here, you can fit something here, and you can fit something there. It's like a multifunctional atom where you can actually attach different things to it, or you can have two down here, two up here, and you can have two double bonds. It's you know, when we say life is carbon based, it's because that molecule is really good at joining things together. So here's a few examples. Here's ethane. Okay, carbon. You'll see that carbon forms the sort of central spine of a lot of molecules, and we'll come to see that in the biomolecules unit. And what I posted on the first slide was, what do you see? Now I'm hoping that you can see that there's carbon, and it just joins with nitrogen, which joins with hydrogen, two hydrogens, etc. And it gives you a bit of more of an idea of how these atoms join together. The double line tells you that that's a double covalent bond, which means they're sharing a pair of electrons each. And what actually this is how proteins are made, how two amino acids join together. But once you understand the atomic bonding of it and what a structure of an atom is, then when I show you what an amino acid looks like in the next lesson, you should think, oh, I understand that, and it should light up, because actually, you know, when we're explaining the structure of a protein, which is on your assignment, you then understand exactly why things join together like they do. All right, so that's it. I'm hoping that went in quite well. Let me know your feedback.